Hey class, today we're going to continue on with Chapter 8, Section 2. In the last lesson, we learned how to draw Lewis dot structures for things that followed the octet rule. And we're going to kind of build off what we learned in the last lesson and talk about two things. The first thing is polyatomic ions, followed by some things that do not follow the octet rule. So what exactly are polyatomic ions? Polyatomic ions are defined as covalently bonded groups of atoms with either a positive or a negative charge. So for example, remember covalent bonds are nonmetals. If we look right here at nitrite, we have two nonmetals. We have nitrogen and two oxygen, and when they bond, they actually bond and have a -1 charge. This negative charge is what makes it an ion. The other thing to know is it says polyatomic. So poly means more than one atom. If we look at all these examples of polyatomic ions, it is two different atoms that are bonded together, and again, they have a charge. One thing to note is that these behave as a single unit, so we always keep them together. Now, most polyatomic ions are usually going to be anions, which means they are negatively charged, but there is a few polyatomic ions that are cations, which are positively charged. And these ions are held together with covalent bonds, but they do still form a charge. So when polyatomic ions combine with another element, it happens during ionic bonding. So these compounds are really cool because they include both ionic and covalent bonding. A good example of a polyatomic ion is ammonia. It's actually a polyatomic cation because it has a +1 charge. The way it forms is a hydrogen ion actually attaches to the unshared electron pair in ammonia, which has the formula NH3. So if we actually look down here, nitrogen, we have 3 hydrogen off them, and then nitrogen has this little lone pair or unshared pair. Well, this hydrogen, which has a positive charge, wants to make sure it has 2 electrons. So it kind of attaches over here, but it gives the entire structure a +1 charge. So how do we actually draw things for polyatomic ions? One, to draw the structures for polyatomic ions, we're going to actually follow the same steps that we learned in the last lesson. The only thing that we kind of have to change is we have to add or subtract from the total electrons based on its charge. Remember, if you have a charge that is positive, just like in Chapter 7, that means that we have lost electrons. So if we have a +2, that means we have lost 2 electrons. Oppositely, if the charge is negative, that means we have added electrons. So if you get a -3 charge, we should be adding 3 electrons to the total. We're going to continue to follow the steps for normal that we've learned in the last lesson. However, when you end, we're going to put brackets around the structure and place the charge on the outside. Here we're going to look at an example together. We have H3O with a +1 charge. This forms when a hydrogen ion is attracted to the unshared electron pair in water. And so what we're going to do is we're going to actually draw the structure for this. First, we have to add up the total amount of electrons that we are allowed to use. Here, hydrogen has 1 valence electron, but there's 3 of them, so I am working with 3 electrons. Oxygen is in group 6, so it has 6 valence electron. And then we have to take into account this plus sign. That plus means that I have lost an electron. So right now I'm starting with 9, but I have lost an electron, so I'm actually only allowed to draw 8 electrons when I draw this structure. Then we have to determine who is the central atom. Now, hydrogen is listed first, but if we go over our rules from our last lesson, hydrogen and halogens are not usually going to be in the middle. So we're actually going to find oxygen is going to be in the middle, and we have 3 hydrogens that are going to be bonded off of it. So I'm going to bond all 3 of these hydrogen, and we're going to see how many electrons we used. We used 2, 4, 6. So when I subtract my 6, I'm left with 2 electrons. Based on our rules, it says make the outside atoms happy first, But if I look on my outside atoms, they're all hydrogen, and hydrogen is okay with 2 electrons. And it already has those 2 electrons from the bond that is being made. So if we've already made all the outside happy and I have some left over, we put them on the central atom, which is right here on oxygen. When we do that, we have to then make sure that everything meets the octet rule. And so here, hydrogen's happy, oxygen's happy, because there's 8 around oxygen. Then we have to make sure that we put brackets around it when we're done, because this is an ion. And then we're going to put a positive sign. And that just means this structure has a positive 1 charge. And that's it. Let's look at these 2 other structures as well. So here we have chlorine. So chlorine has 7 valence electrons. Oxygen actually has 6 valence electron. And that -1 means that it has gained an electron. So we're going to add 1 to this structure. So we end up adding, and we have 14 electrons total that we're working with. Then we need to decide who is the central. Well, since there are only 2 atoms, there cannot be a central atom. It's just going to be chlorine bonded to oxygen. In order to make that bond, we actually used 2 electrons, which leaves us with 12. Then we're going to make sure everybody's happy. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have placed those 12 electrons, and I'm left with 0. Then we need to make sure everybody's happy. Chlorine has 8 around it. Oxygen has 8 around it. Both of them are happy. Because this is an ion, we have to make sure we put brackets. Notice brackets, not parentheses. And put that -1 charge on the outside. If we look down here with NO3 with a -1 charge, nitrogen gives me 5 valence electrons. Oxygen gives me 6, but I have 3 of them. So 6 times 3 actually gives me 18. From there, we have a -1 charge. That means I've gained an electron. So when we add all of these up, we want to make sure that we take all of that into account. So 18 plus 5 gets me 23, and then that 1 gets me 24 electrons that I'm working with. We're going to figure out who goes in the middle. Nitrogen would go in the middle. It's listed first, and it's not a hydrogen or a halogen. Then we are going to bond, it says 3 oxygen off of it. So 3 oxygen. With making those 3 bonds, I've actually used 6 electrons, which leaves me with 18. From there, we're going to make the outside happy first. So oxygen has 2, but if I add 3, 4, 5, 6, 7, 8, that gives me my 8 here. And we're going to put them around this oxygen, and last but not least, this oxygen. Now we got to figure out how many electrons we used. We used 2, 4, 6, 8, 10, 12, 14, 16, 18. I did that and I did not go over. I have exactly 0. Then we have to make sure that everybody's happy. That is usually the rule everyone forgets to do. While all my oxygen are happy, my nitrogen's not. My nitrogen only has 6 electrons around it instead of 8. So what's going to happen is we're actually going to take a pair of these electrons off an oxygen. It does not matter which oxygen. We're just going to choose this one, and we're going to make a double bond. And we're going to finish it out by putting brackets around it with a -1. Then there are a few things that are exceptions to the octet rule, which means they are going to either have an odd number of electrons, so that is a good example. They could also be things that are okay with having less than a complete octet, so instead of having 8, they could be okay with having 6 electrons around it. And then there are a couple things that are okay with having more than 8 electrons. A good example of when we see something that has an odd number is the structure NO2. It has a total of 17 electrons, And so when we end up drawing this structure, it's impossible for it to satisfy the octet rule for every single atom. Yet this molecule still does exist. It is still a stable structure. Now, I will never have you on your worksheets ever have to draw one that has an odd number of valence electrons. I just want you to know that these do exist and they are stable. However, there are some molecules that have an even number of valence electrons, such as boron, but they do not follow the octet rule. I'm going to go ahead and start this. You will have structures in your homework where boron is drawn, and boron's actually okay with just having 6 electrons instead of having a full octet. And that's okay. It will not have to make a double bond. So here is an example of boron, and it has 6 around it. Notice there was not a double bond that was created because here it's bonded to a halogens, and halogens do not like to make double bonds. Boron's just really one of those weird ones that's okay with having 6, kind of like hydrogen is okay with just having 2. There are also a few atoms, such as phosphorus and sulfur, which are infamous for having something called an expanded octet. These things are okay with having more than 8. So, for example, phosphorus usually can go up to 10, and sulfur can go up to having 12 electrons. A good example of this is sulfur hexafluoride, which has the formula SF6. As we note here, when we look at it, sulfur actually has 2, 4, 6, 8, 10, 12 electrons bonded off it, and that's perfectly okay. This is still a stable structure. Sometimes we'll also have more than 8 off of an atom because anytime we have any extra lone pairs and the outsides are happy, we always stick them on the central. That's part of your initial rules that we gave you when we were learning how to draw Lewis dot structures. And this happens quite a few times. And one of the examples this happens with is xenon tetrafluoride, so XeF4. We can see that we've made the outside happy, so all these fluorines are happy, and we have leftover electrons, and so we ended up placing them here on xenon in order to use them all up, and this is also still a really stable structure as well. So here we're going to have a few examples that we're going to do, and so the first one we have PCl5, which is phosphorus pentachloride. Phosphorus has 5 valence electrons. Chlorine has 7, but 7 times 5 gets me 35. So I'm working with 40 total electrons. Just like when we were drawing normal Lewis dot structures, we still have to add up those electrons we're allowed, and we still have to determine the central atom. Our central atom is typically the first one listed, so that's going to be phosphorus, and we are going to bond 5 chlorine off of here. It is okay that we're bonding 5 chlorine and phosphorus has more than 8. It is still stable. So making these 5 bonds, we used 2, 4, 6, 8, 10 electrons, which leaves me with 30. Just like your normal rules, you're going to make your outside happy first. So each of these chlorine are going to have to get 6 electrons. So I used 6, 12, this one gets me up to using 18, 24, and then over here we end up using 30. So that brings me down to 0. Please note when you're placing these electrons, they are over here where there are no atoms. If you place your electrons right here, that's considered bonding and you cannot do that. So we want to make sure we place the lone pairs around it that's not near another atom. Once you get down to 0, check to make sure everybody's happy. All these chlorine are happy. Phosphorus has at least 8 around it, so it's happy, and so this is considered the correct structure. And then our last example, chlorine and 3 fluorine, so chlorine trifluoride. Chlorine gives me 7. Fluorine also gives me 7, but there's 3 of them, so that gives times them, we get 21, which gives me 28 total electrons that we're working with. Here, typically I always tell you halogens cannot go in the middle, but this is only halogens. So unfortunately, the one that's going to go in the middle is the one that's listed first. It is bonded to 3 fluorine. In order to make these original bonds, I had to use 6 electrons, which means I'm left with 22. you are going to make the outside happy first. So here, we're going to make the outside O happy and have 8 around it. When we make fluorine happy, we end up using 2, 4, 6, 8, 10, 12, 14, 16, 18 electrons in order to do that. And that leaves you with 4. And so oftentimes people recognize that they need to make chlorine happy, so they do put 2 more on here. However, if we would still have 2 left over, and anytime you have extra left over, they're going to go in the central, even if that puts them above 8. So here we're going to put both pairs up here on chlorine. When you're placing electrons, please make sure they stay in pairs. So here we're going to add 4, and that leaves us with 0. This is still a correct structure because all of them meet the octet rule, and chlorine has at least 8, so we're happy. And that's the end of today's lesson. If you have any questions, please let me know, and I hope you guys have a great day.